to briefly say what we did last time. So the idea is to study Joaquin tidal bond gravity on a disk, Euclidean disk, interpreted as a Euclidean black hole, and we saw that the theory by itself has some issues, and one needs to find good UV completions. One way that we will see is in as sectors of higher dimensional black holes. Another good completion is as a sector of SYK. And the one that I started mentioning is when you sum over topologies, the UV completion, so to speak, is a matrix integral. Okay. So to summarize, I explained the prescription of Schenker-Stanford to compute the sum over topologies, and it's evident, or we will see that it's evident that the theory is equal to a matrix integral in the sense explained by this equation, that each path integral with certain holographic boundary conditions is equal to a thermal partition function of some system with a Hamiltonian H, but the new feature is that you have to average over Hamiltonians with some measure. And this measure has some formula, but the only thing we need to know is that there is a one-to-one map between this measure and the disk density of states, that in the case of JT gravity is this sinh square root E formula that I explained last time. Okay, so first I want to say a couple of words about how the duality works. So the matrix integral is not literally it's a matrix integral, but it's in the double scaling limit. So I just wanted to briefly say what that means. So if we have an integral over L by L matrices, at large L there is a Toft expansion. So there is an expansion in 1 over L. And this genus at this point is not the genus of any gravity theory. It's interpreted as the genus of the Feynman diagrams of the matrix integral. And in the simplest case, there is usually the leading contribution in the disk, meaning with n equals 1 and genus 0. It usually is described by a density of states that is what is called the one cut. So the density of states is non-zero and has some random shape like this on a finite interval. And this is the usual behavior of this matrix integral at large sizes. You can have multiple cuts, but for the purpose of this talk, we'll only look at one cut. So what is the double scaling limit? So here I show one example, which is a matrix integral with a quadratic measure. So this is so the measure is e to the exponential of the potential of the matrix, and here the potential is quadratic. And this can be solved exactly. This is the Wigner semicircle, and it's given by this formula, which is the, semicircle of length to A. And A is basically a parameter of the potential, so it's like the Toft coupling in the way of the potential. And what the double scaling limit means is to, in this case, take the parameter of the potential A to infinity. And in a sense, what we are doing is zooming into the edge of the distribution. So we go from a finite distribution like this to a double scaling limit where we are only looking at the edge, that in the case of the quadratic potential is a square root E edge. And this, if you remember, this is the small energy behavior of JT gravity, so it's not completely unrelated. And actually the square root of E is universal for matrix models. It's understood by Wigner. And what we will compare with e to the s naught is not L, not the size of the matrix, but it's a parameter that appears in the double scaling limit, which, for example, in this case, we take A to infinity, L to infinity, but we keep this combination fixed, and this is e to the s naught. So e to the s naught is some parameter of the density of states that should be thought of as large, and it's in terms of, and you should think of as describing not the size of the matrix, but the average level spacing of the eigenvalues in each realization.
Can I check this point? So S0 is not counting state there.
Yeah, so e to the S0 is not the size of the matrix. Yeah. you have to take this double scaling limit.
So for instance, I mean, it cannot be interpreted as zero or ground state, number of ground state, something like that.
No, that's something that it's a wrong interpretation of H0, because if you remember, and you can see that even in the disk. Actually, I have the picture here. So if you look at let's say in SYK, you look at the low temperature behavior, and you find that let me see, the entropy is S naught plus something proportional to T. And this you might think like, okay, you take low temperatures and you have this large degeneracy of the ground state, but that's not what happens, because you know that you have another term from quantum effects that is basically a log T. This is very important. And rho, the density of states, as you take the energy to zero, it's actually going to zero.
Mm.
So the naive semi-classical picture would be something that does like this, where you go to zero and you have a large zero temperature degeneracy. But quantum effects, here quantum effects are large as you lower the temperature. And this makes the curve go down. And for example, in
so this is even true when we do the dimensional reduction or from higher dimensions by taking extremal extremal limit of Rn black hole, something like that.
Yeah, I will talk about that later. I think it is, but the subtlety
it is not counting state. Their extremal state, something like that. It cannot, in general, interpreted as a counting extremal entropy, something like that.
Yeah, in the case of higher dimensions, I think the extremal area should not be interpreted as counting the extreme number of extremal black holes for a similar reason. But there is a subtlety that the answer depends a lot on what kind of symmetries you have in your theory. So
okay. It depends upon the situations. Supersymmetries or something.
Yeah. So in the end, I will mention that when you have supersymmetry, this parameter S naught actually is the number of microstates.
Okay. Thanks.
Yeah, sure. Okay. So okay. So well, this is what I said before. So the expansion is on this e to the S naught, and you should think of it that like there is some curve that we are zooming in the edge. Yeah. Okay. So I will go over this quickly, but I'll just ask me if you're interested in more details. But what I just want to say is that there is something called the loop equations. So these are Schwinger-Dyson equations of the matrix integral, in the sense that they arise from the invariance and the reparameterizations of the matrix. And this is an example. So this, I think it started with Migdal in the 80s, and then it was improved over the years. And this is an example which relates the partition function with the two partition functions. So of course, this is a kind of useless equation until you do an expansion. In this case, at large L or at large e to the S naught. And when you do an expansion, then because of large L factorization, things like that, then it becomes useful, and it actually produces a recursion relation that you can solve. And this evolved in the years until I think the work of Einar and Orantin made it the most, or they give a very nice formalism to understand this recursion. So I want to make some comments that I think might help if any of you is interested in looking at the paper. So the idea is the recursion is given in terms of the resolvant, which is this. So this is, you should think of as a Laplace transform of the trace. So the observable we are interested is the trace of e to the minus beta h. But if you do an integral over beta, you can. So these two are related by an integral transform. That's what I want to say. So one is fixed. If you know one, you know the other. And this resolvant correlator of the solvents, you can think of it as some like fixed energy boundaries in a way, and you can expand it in e to the S naught in the same way, and the coefficients will call RGN. And people talk about the spectral curve that is usually defined in, where is it? Well, in this way. So you define this coordinate C, and this is because usually the density of states has a branch cut, where when the density of states is non-zero, there is a branch cut. If you remember, it was square root E, for example. So it's useful to define these coordinates C, and then you define the spectral curve as x of C being the well, this is the formula, and y of C is proportional to the disk density of states. And it's customary to define the resolvent as this WGN, which are just proportional to the coefficients of the resolvents by this factor. This is just convention, but it's useful. So the recursion relation that Einar and Orantin gave was in terms of this WGN. And if you remember, the Laplace transform of Mirzakhani's volumes was also given in terms of this WGN, and that's how you make the match, the comparison. And okay, this is the recursion, and the only thing to notice is that it's the same formula as before for the Laplace transform of the Bell-Peterson volumes. And if you remember, there was some function, there was a sign of C that appeared there that fixes the spectral curve or fixes the density of states of the matrix integral. And the one you need to produce the volumes is the same as the ones that JT gravity gives you. So that's the non-trivial aspect of it. So this is, okay, I wrote here again. So this is the density of states of Joaquin Teitelbaum. You derive this spectral curve, and this is the same as what's required by Mirzakhani. So then this proves the correspondence that we claimed at the beginning of the talk. Okay, so this is just a reiteration, but yeah, as I say here, the only thing I wanted to stress is that the Sachenka and Stanford says that pure JT gravity is holographically dual to a matrix integral, where now you have to interpret it as an average over Hamiltonians. And this is different of previous ideas that connect 2D gravity with matrices, because the matrix is usually interpreted as some kind of triangulation of the surface where the 2D gravity lives. So the new thing of Sachenka and Stanford was to think of it as an ensemble average over theories. Well, a quick comment here, but we talked about it yesterday, so I will be brief. But these Euclidean wormholes. So this is the Euclidean wormhole that is the leading one that is responsible for the lack of factorization that can be explained by an ensemble average. And this has been studied over the years, especially in these two papers. And the idea of Euclidean wormholes introducing randomness of coupling constant was even observed before by Coleman, Giddens, and Strominger in the 80s. And I think this work, and also the role that these Euclidean wormholes play in the calculation of the page curve, kind of emphasize the question of how are we supposed to understand these contributions and what happens in models of holography where we know the theory to be dual to a single, let's say in equals 4, for example. But okay, these are open questions that have been asked a long time ago, but I think now is a good moment to try to think of it more seriously. Okay, so now we talk about the formations of JT gravity. Maybe is there any question?
Yeah, may I have one question?
Yeah.
Yes, so to create a boundary, you introduce this exponential of minus beta h, where h is the Hamiltonian, which is integrated over. And my question is, what is the meaning of this Hamiltonian? Is there any kind of physical quantum states living somewhere, and you think about the average of these quantum systems?
Yeah, the Hamiltonian is the description of the quantum system itself, right? Living in the boundary. So to give a quantum to define the system, you need to give the Hamiltonian and compute the thermal partition function, and that's what you're doing. Maybe the thing that might strike a little odd is that I'm talking about the Hamiltonian and I'm not giving like some kind of fundamental degrees of freedom.
Right.
But you can think of SYK in that way as an example. SYK you can think of as a very complicated matrix integral, because when you integrate out the fermions, what you end up is with Hamiltonians that are matrices that are very sparse. and with some particular combination of the J's of the couplings.
Mm.
And then when you integrate over J, you're kind of integrating over an matrix ensemble that is very special. So in that sense, it's nothing weird.
So my confusion is that so on the boundary you have Schwarzian degrees of freedom, right?
Yeah.
And then, but you are not making an average of possible Schwarzian degrees of freedom.
Mm-hmm.
It's different. So
It's different.
you brought in something different, well, large class of Hamiltonians, then you make integration over it.
Yeah.
If you call it just a matrix, then I'm happy with that. But if you say that it's Hamiltonian, then yeah, I'm concerned with what kind of quantum system we are averaging over and how it was derived from, say, JT.
Yeah. So it was derived from JT in the sense that JT told you what the measure is, or the probability distribution for each Hamiltonian. And if you look again as an example, SYK, yes, so SYK has a nice feature that you have this description with fermions that make it a little bit more transparent. And the Schwarzian is just a mode that emerges in some limit. Just like when you take large S naught and temperature to not be too low, then the disk is going to be a good approximation. But in general, it's not. In general, it's this complicated Hamiltonian with the fermions and all that.
Oh, I see. So it's a kind of generalization of Schwarzian to the case of. I see.
Yeah, if you want to think of, you can think of the Schwarzian maybe as a bulk object, that maybe kind of emerges in some limit in the boundary, but it's not an exact statement. Just like in SYK, right? If you go beyond low temperatures in SYK, then it's not a good approximation anymore.
Okay, thank you very much.
Sure.
Can I ask about this Euclidean wormhole geometry?
Yeah.
In JT, basically, this wormhole type configuration is off shell, right? And well, there are examples where we have Euclidean wormhole solution
on shell
in certain cases. Yeah. And do you think there are some differences in their interpretation?
No, I think that's an open question that would be very nice to understand better. Like maybe, yeah, it would be nice to review these Maldacena-Mao solutions to understand whether they are stable or not, if they really contribute to the path integral. And if they really do, and there is nothing canceling them, then you would say that there is something wrong with holography, maybe, because at least the examples that they give, they are dual to single theories. So I think the most likely is to understand, if you believe in holography, that probably those solutions might not contribute. Maybe they are not in. I mean, the fact that you find it, well, yeah. I mean, okay. Short answer is, I think it's an open question. It would be nice to understand better. Yeah.
Okay.
Yeah.
Okay. Thanks.
Sure. But it's definitely one of the main things to an important point. Yeah. And even in 2D gravity, if you have something that you expect to be dual to a single theory, then one option is, are you supposed to not include these geometries, or maybe you have extra contributions coming from UV physics that cancel them, or not cancel them, but just restore factorization. And yeah, that would be great to understand. But okay, yeah.
Okay, may I ask? So yeah. I'm not so familiar with this matrix model, but how unitarity of the system is ensured from this in this partition function?
No, unitarity is just because it's an integral over Hermitian matrices, and the Hamiltonian is Hermitian, so. Yeah.
So you may still even we are summing over this spectrum, but somehow. So if the Hamiltonian is not Hermitian, then the unitarity is broken. Is this correct?
Yeah. So if you define a 2D theory that and actually we might see an example. If you define a 2D gravity theory that you find to be dual to an ensemble where you integrate over matrices that are not Hermitian, then probably you would say that the boundary is not unitary, right? Because
I see.
yeah.
Okay, thanks.
Yeah, sure. Okay. Okay. So the last thing I want to say about 2D gravity before moving to 3D is about deformations. So we will consider JT gravity with defects, and two motivations is to generalize this story to more general dilaton gravities, as I think Johannes was asking yesterday. And another motivation is an application to 3D gravity that I will mention later that we did with Henry Maxfield and some independent work by Witten. But okay, so the idea is to, and this will become clear later, we were going to allow the presence of defects in the metric, and we will sum over the location of the defects and any number of them. And this introduces two parameters. One is the deficit angle, theta, that I will parameterize in terms of alpha. So alpha equals 0 means a cusp, and alpha equals 1 means no defect. So 0 deficit angle. And this lambda is like a fugacity. So whenever you have, if you have one defect, it comes with a factor of lambda. If you have two, lambda squared. So it's like a fugacity of the defect. And the calculation goes the same way to the path integral. So as long as alpha is smaller than 1/2 or the deficit angle bigger than pi, then there are always geodesics homologous to the boundary. And this means that we can still cut and glue the geometry in this way, where now the defects are in this region, and we need to compute the Weil-Peterson volume over moduli spaces with some number of boundaries of lengths B1 to Bn, and some number of defects with angle alpha 1 to alpha k, where k is the number of defects. So why is this restriction of alpha important? So here I'm showing two examples with alpha smaller and bigger than 1/2. In the case of smaller than 1/2, this is a hyperbolic surface with two defects. And you can see that there is a geodesics, obviously, from, well, not obviously, but at least intuitively from the geometry. But if the angle is too big, then you get metrics, hyperbolic metrics that look like this. And now there is no geodesic. So the Sachin-Stanford recipe cannot be applied there. So we will restrict to alpha smaller than 1/2 for now. So the only new ingredients is the one defect partition function. So this we computed with Thomas Mertens and a lot more detail by Witten. You can do the same. You integrate out the dilaton. You localize to a theory with one to a hyperbolic metric with one defect. You reduce to a Schwarzschild mode. You apply localization and you end up with this answer. So this is like a semi-classical contribution, and this is like a one loop contribution. And the reason why here you have beta and not beta cubed is that now this geometry has only a 1-0 mode related to rotations along the defect as opposed to 3. And the density of states that you would derive from this contribution has this form. Yes. And then you need the volume, as I mentioned, with defects. And this is a result that in this range that was shown in these two papers, that all you need to do is just replace a defect by a geodesic boundary, and then analytically continue on the length. And for each geodesic boundary that you add instead of a defect, you replace it by 2 pi I alpha. And if you compute the Weil-Peterson volume, for example, here I have n boundaries, k defect. So, and the defect have parameters alpha. I compute the Weil-Peterson volume with n plus k geodesic boundaries, and the extra boundary that I added, I analytically continue in this way. This is clear? Okay. This is just the math result. And okay, so this is roughly how the calculation looks like. So you have an expansion in genus and number of defects. And here I'm allowing the possibility of having several species of defects labeled by their own lambda I and alpha I. this corrects the overcounting from the Weil-Peterson volume of identical defects. And here you see that each species is weighted by this lambda to the k. That's why we call it the fugacity. And each contribution is, again, we glue trumpets to the Weil-Peterson volume with this number of defects. So this is an example of the partition function with one boundary. And now this would be Chetty gravity. And now we need to add one defect for all genus, two defects for all genus, etc. Okay, so the main question is this dual to a matrix integral? And can we get the new density of states? Like I was mentioning yesterday, a useful thing is that you can actually resum over k and get a closed answer that you can study. And the answer is yes. So you can do it, and also it is dual to a matrix integral. And
so Joaquin,
yeah.
Sorry to interrupt. Can I ask some questions? So it's not so the statement is that these defects somehow deform the Joaquin tidal volume gravity?
Yeah, I'm going to mention that in the end. Like first I wanted to solve this theory, and then I will mention the
okay, thank you.
Yeah, sure. Before I go to 3D, I mean, something that will be useful later is here you can ask a question, can I define a theory where I sum over a finite number of defects? Why did I sum over any number? And you can see that when you define over a finite number of, when you sum over the finite number of defects, then you get answers that are ill-defined. And this is related to something that we will see in 3D. So the idea is that this is the one defect correction to the partition function, this formula that I shown before. And at very low energies, it gives something that diverges. And this is problematic if lambda is positive, and it's even more problematic if lambda is negative, because it will produce a negative density of states. Yeah. But when you sum over defects, very close to the edge, this is the contribution from two defects. And if you compute 3, 4, they all diverge faster and faster as the energy becomes lower and lower. And they resum into a square root edge with a shift of the ground state energy. So this is a small motivation of why we want to, if we would stop at any finite number of them, we will find things that blow up too fast. Okay, and to sum over the number of defects, so now I want to give the result after summing over the number of defects. We need some knowledge about Weil-Peterson volumes at genus 0. So, okay, so it doesn't matter the details, but I just wanted to point out that we used the formula that we derived with Thomas Merton. Yeah.
Do you have any idea what is this low energy excitations look like?
What do you mean? Sorry.
So you say that density of states are divergent in low energy?
Yeah.
And then I just want to know what kind of excitations are these? Why they are so densely populated and so on?
I don't know how to give a more intuitive picture. It's just the way that the one defect behaves yeah. So this just comes from one defect. So how to say it? Yeah, I'm sorry, I don't know how to say it in a different way, but you just look at what happens when you include one defect, and the correction from one defect becomes
so then
at low energies. But
the origin of this 1 over square root t.
So what is the origin of this?
Yeah, technically, just if you don't have just a physical picture, maybe technical, maybe origin is also helpful.
Technically, they come from the way the Weil-Peterson volumes grow when you take the boundary to be very large. So here we are looking at, so when you integrate, here I'm doing one boundary, so I integrate the trumpet, and I have the Weil-Peterson volume with, let's say, one boundary beta and two defects alpha and alpha. Here the dependence on alpha is not important, but this thing grows with B to some power. So when I take energy to be small, I'm taking beta to be large, and with beta is large, the size of the boundary is very big. So this integral is dominated by very large values of b.
I see. So
And this volume grows too fast at large.
that the bigger the boundary is, the easier it can be excited.
Yeah, you could say that. Yeah. So this divergence is for when the boundary becomes very large. Yeah.
I see. So that is the picture. Okay.
Okay. Yeah.
All right. Thank you.
Yes. Yeah. Okay. Yeah. So okay. So I was saying to sum over defects, we need this. We need to know the formula for the Weil-Peterson volumes in the disk. And yeah. So with Thomas, we derived this formula. We did it from the physicist derivation from the minimum string, but apparently it can be derived from first principles. That's work in progress by Timothy Ball. And it's given in terms of derivatives of this function u of x, and this function is defined in this way. And this will appear a lot of times, but and we replace a border by a defect in this way, and we sum over defects, and we get this final answer. So I'm sorry, it's not a very, I don't know, we couldn't get anything simpler than this, but it's good enough. So this is an integral of over u. It's very interesting that the defects appear linearly. So this comes after summing over any number of defects, but here we only have a term linear in lambda. But this E naught, the new edge, is found by solving this equation. So there will be a lot of non-trivial dependence on lambda implicitly through E naught. So what I want to show, well, actually, will be in the next slide. Okay, so here I'm summing this number of defects in the disk as I was mentioning. And this integral is easy to compute numerically, and you get formulas like, you get shapes like this. So, so here is for lambda negative, you see that it goes to 0 at some non-zero value. When lambda is positive, again, it's smooth with a shift in the edge. But if lambda is too big, in this case, it's, okay, this is a small number, but it's order 1 in the sense that it's not going to 0 with, I don't know, S naught or anything. For a critical value of lambda, you start getting weird things like this negative density of states. And related to the previous question, maybe I would say that here, this would not be dual to a unitary theory. So if you try to make a matrix integral that would give you a density of states that is negative, you probably won't do it with the Hermitian matrices, of course. But the interpretation of what happens for such values of the fugacity is an open question. We don't understand very well. Okay, so now I have a calculation that I will skip, but I put it there in case anyone want to ask. But there is a universal formula for the two-loop, for the double trumpet from the matrix model, and it's this. And when we integrate over defects, it's not trivial that if we want it to be a dual to a matrix integral, that we want to, that it still satisfies this equation. But okay, well, you can sum over defects using this formula, and I'm going to skip, and you can see that that's true. So I put it there if anyone wants to ask later. But the main point is that we can repeat this calculation of summing over defects for any number of boundaries, and we get the formula like this, that again is in terms of a function u of x. And now the u of x that I will call string equation has this term that corresponds to JT gravity, and this is the term that corresponds to one defect. And this result at genus 0 for any number of boundaries is the general answer for a Hermitian matrix integral in the double scaling limit found by these authors. And the name string equation comes from the old literature from the 80s on matrix integrals. And all you need to know is that there is a one-to-one map between u of x and the partition function. So if you give me u of x, it's the same as giving me the disk density of states or giving me the potential of the matrix. They're all equivalent description of the matrix ensemble, and in particular related by this formula. Okay. So we check that this is a matrix integral for genus 0. So there is a theorem. I'm not going to explain it, but there is a result that tells you that this is true to all genus. And the idea is that if you give me something that solves the topological recursion, which is this W old, then you can construct new resolvents that still satisfy the recursion relation, this W new. And you can do it in this way. So this is a theorem of Einar and Norantin. So if you give me a function f and a contour gamma, yeah, and a parameter lambda, then this W nu will still solve the topological recursion. So we will still be describing a matrix integral. And in the paper with Henry Maxfield, we show that there is a choice of gamma and f that makes this sum be exactly the sum over defects. So the JT gravity with defects is an example of this deformation theorem of Einar and Norantin. Okay, so here I'm just a summary. So we have the, well, this is the same as I said before. But the main point is that JT with defects is still dual to a matrix integral in a holographic sense. And the matrix integral is still interpreted as an average over Hamiltonians. And what the difference is now that the JT gravity had a matrix potential or a matrix measure over Hamiltonians, and now you have a two-parameter generalization. So the matrix potential will depend on lambda and alpha, and it will be different than the previous one. Okay, so to finish this discussion, so as Johannes was asking, so what is the relation to the dilaton gravity? So in this papers, we argue that inserting one defect in the JT path integral is equivalent to inserting this operator. And you can see that if you integrate out the dilaton, then in JT, JT has a term that goes like phi r plus 2. And if this is exponential in phi, phi still acts as a Lagrange multiplier. So the equation that it imposes r plus 2 will be modified to this. So okay, from this approach, you can see that this observable is the same as inserting one defect. And this coefficient is related to the deficit angle that you will have in the same way that I described before. And when you have multiple defects, you just have to sum over these insertions. You can insert each of them independently and integrate over their position. And now you can resum over K, and this insertion just exponentiates here. And here I put these two dots because there are some subtleties of you are kind of defining these operators in a quantum mechanical way when you define what to do with the contact terms when two defects collide, etc. But so this quantum definition just means that we define it in a way consistent with the definition of the volumes and calculation that I described before. So the net effect is a shift of the dilaton potential. So what we have solved is a theory of 2D dilaton gravity with a generic dilaton potential of this form for alphas between 0 and 1/2. And okay, just a quick comment. So this is some work in progress, but you can repeat the calculation for alpha bigger than 1/2, and you get this ugly answer. But everything you need to know is that this function, this is giving you u of x. So knowing this is equivalent to knowing the density of states. And this shows that in the papers you might, I think in the paper of Witter and ours, if I remember, I think you might see claims that we hope that this answer is analytic for all alpha, but it seems like it's not the case. So it's very special for alpha smaller than 1/2 that you get a simple answer. And the issue is here, right? So as you move alpha from 1/2 to 1, you have to more and more orders in lambda.
Joaquin,
excuse me?
Yeah.
Sorry, go ahead.
Okay, sorry, thank you. So before you mentioned, like, so the calculation is perturbative in lambdas initially, but then you resum, right? And so then the answer is valid for finite lambdas as well.
Yeah.
But in principle, can you exclude the possibility of like non-perturbative contributions, like 1 over lambda or something like that?
No, not really. No. I mean, one thing is that at least the sum over lambda over K converges, as opposed to the genus expansion, that, okay, that's something that I didn't talk about, but the genus expansion is asymptotic. So there is a lot of non-perturbative ambiguities of how you define this. And that's related to well, okay, whatever. But yeah, the sum over k is conversion. You don't need to add anything else, but you could still add it. And maybe the question is what the gravitational interpretation would be of adding different. But yeah, thanks.
Thank you.
Can I ask? So in the so phi looks like has some periodicity for phi to some I times integer. Is there any reason for why this exponential 2 pi phi is important?
You mean here?
Yeah. So this combination of 2 pi times phi looks special, and
that's just so here you could have called this. I don't know what letter. Could have called this y, some number, but the point is that this appears in whatever multiplies the delta function is the deficit angle. And
I see. So
I just decided to call the deficit angle to parameterize it in terms of alpha because it simplifies some formulas, but
okay,
yeah.
Thanks. Yeah.
Thanks. That's fine. Okay, so that's all. So I have a little calculation here, but I will skip it. So okay, as a summary, we have that a lot of theories of this form are dual to matrix integrals in this way. And these are some open questions, but I think I will skip them because of time. But maybe the only main two questions I would like to know is how to generalize this with matter, and if we can find some better defined models of 2D gravity with evaporating black holes where we can compute the page curve. And also how to go away from the double scaling limit. That would be interesting. But okay. Yeah, I mean, they're all, I think the PDF is in the website. So if you have any question, we can talk about that later. Okay, so now we'll start with the application to higher dimensions. So, okay, maybe it's a good time to, if anyone has any further question about 2D.
So may I have?
Yeah.
Can you write down a boundary theory from your defect case? So JT plus defect, can you, I mean, yeah, as in the without defect case. So how the SYK can be deformed in the presence of defect? Can you answer that?
Well, I mean, you compare SYK with JT when you compute things in the disk.
Yes, right. So if I repeat the same calculation, how the defect can be, yeah.
Oh, you mean if I want to keep lambda to be not small, but to...
I mean, I want to ask Schwarzian plus some, yeah, that's what I want to ask. What is it? Can you answer that?
Yeah, I'm not sure. I didn't think about that.
Okay. Then, but, okay, my second question, simply, I think I missed what is the corresponding dual matrix integral?
Oh, the dual matrix.
Sorry, yeah, I simply missed it. Yeah.
Yes. So do I have it here? So yes, I should have written.
In the case of defect, yeah.
Yeah. So we have a dilaton potential, or if you define with the defects that depend on two parameters, lambda and alpha.
Yes.
So now here, the only difference is that you have a measure that depends on lambda and alpha, meaning that this is some e to the minus trace of BH. And this has a very concrete formula in JT that it's responsible for the density of states being the sinh square root t in the disk. And now you just have to trace back what dilaton, what matrix potential corresponds to the JT plus defect density of states.
Yeah.
And it will give you some formula. I didn't write it down because it's more ugly combinations of Bessel functions, but you can compute it.
I see. I see. I see. Thank you.
Sure. Okay.
I have one stupid question to make sure. my understanding. So in SYK, we have a disorder average, and here you have average over some Hamiltonians. And are they, in what sense they are related, or they are completely unrelated?
No, they are exactly the same.
They are the same?
They are the same because the disorder is the same as saying that. So that's what I was trying to say before. So let's say you write the Hamiltonian of SYK and you choose some basis, whatever. Yeah, you choose some basis. Then it's just a big matrix, right? With a lot of zeros and a lot of entries that depend on J. So the integral of disorder over J, you can think of it as integrating over matrices with a very complicated measure that it's outside of this form. That is not simply this. So this integral over H is like an integral over J. But if you would, so you can write the SYK partition functions in this way, but what you would call mu of H would be super complicated. Yes, but in the disorder in SYK is the same as what we mean by disorder here. Maybe another big difference why I think it would be interesting to go away from the double scaling limit is that in SYK you don't have a double scaling limit. So the matrix have a definite size.
So may I understand that in SYK you take a particular limit to get to this matrix integral with a particular form of mu, low energy?
Yeah, so you're integrating over very special types of matrices in SYK, but it has the same structure. Yeah.
I see.
Can I ask you a question?
Yeah.
So if you just consider simplest modification of your theory, like by replacing this trace e to the minus beta h to just h to h squared, like beta 1 h squared, beta n h squared, like that. Do you have any guess what should be the dual action in terms of gravity?
I'm not sure. I mean, that would be a computed by
just a phi squared r and so on. Any trial?
I mean, I guess you could think of when if you do JT gravity with some fixed energy, instead of doing fixed length, you can do JT gravity with fixed energy, right? And then doing trace of e to the minus beta h squared would be to just integrate over energies with that trace of e to the minus beta e squared. So what I'm trying to say is that you could think of that as a different boundary condition. Like this corresponds to fixed length boundary condition, and other functions of h could be other boundary. For example, the resolvent, the trace of 1 over e minus h, or more general functions. You in principle you could map to complicated boundary conditions in JT gravity.
Okay. Thank you.
Question?
Yeah.
Hi, okay.
Hi, how are you?
Okay, thank you. I have a similar question what Koji asked, and here you said this is due to the SYK model, but in SYK model you have to do the random averaging, and you have a lot of spectrum, like a lot of metal, like a degree of freedom. But in JT you don't have it. Right, the low line spectrum you have it, but the other mode is somehow it's hard to see at this setup. But this random averaging is really quite well organized with this all degree freedom. But in JT, if you don't have such a matter, how to?
But you can see them. I mean, for the purposes of this talk, the matter is just a way to generate these very special matrices. that are the Hamiltonian. So maybe what you're saying is that there are also observables in SYK that might not be there in pure JT gravity. And that's true. I mean, I'm not saying that pure JT gravity is the same as SYK.
I see. So
that,
in SYK model, this is quadratic level looks like better, but if you go to the interaction, then it's more than like a usual matter, isn't it? Right. So then in that case, so how JT gravity can incorporate those some?
No, that's part of the open question of generalizing it with matter, hopefully.
I see. Okay.
Yeah. Like if it would be great if I knew the dual of SYK. So then I could answer you more specifically, but maybe one can find something in between, right? Some model of JT gravity with some kind of matter that is dual to some matrix integral. Yeah.
Okay, thank you very much.
Sure. Yeah, so what should I do? Can I continue for 5 minutes or should I just start this?
As you wish. I mean, we could take a break, like, I mean, for half an hour or like, I mean, you can continue if you want and then like, I mean, stop in 5 minutes or so.
Okay.
Like you have like 7 more minutes or so.
I have 7 minutes. Okay, then I will just continue until 6.
Okay.
Or 10, there, sorry. Okay. Yeah. Okay, so now I will go to higher dimensions and where all this, some application of this. For the first part of this part, I will only talk about applications of quantum effects in the disk. So for now, you can forget about non-perturbative corrections. And the idea is, as we talked about yesterday, the near extremal limit of 3D black holes are well described by JT gravity. So first I will talk about, okay, this is, as you all know, this is the Einstein gravity in 3D action. Black holes are given by this metric. This is a metric of the BTC black hole parameterized by R plus and R minus. This I wrote in Euclidean time. And the energy, angular momentum, and Bekenstein-Hawking entropy are given by these 3 formulas in terms of R plus and R minus. So the geometry has 2 horizons. This is the outer horizon, and this is these are the inner horizons, this and this. And in Euclidean space, this is just a hyperbolic disk times a spatial circle. And the horizon is the outer, the center of the disk is the outer horizon. Okay. And just to clarify what language or what conventions I will be using. So I might go between these 3 different descriptions that are useful. One is in terms of the temperature given by this of the black hole, or the angular velocity omega, that is the chemical potential for the angular momentum, which is this. It's also useful to talk about it in terms of left and right moving temperatures, which are given in this and this way in terms of temperature and angular velocity, or in this and this way in terms of the position of the horizon. Or yet the third way is in terms of the boundary of the BTC black hole is a torus, so we can describe in terms of the moduli of that torus, which is Q and Q bar in terms of tau and tau bar, and these are given in this way as a function of left and right moving temperatures. Okay, so we will focus on state of fixed angular momentum and low temperatures, and this implies that the 2 horizons will be close, or well, not they won't be close, but the radial coordinate of the 2 horizons will be very close to each other, and some size I will call R0. So R0, everything with a subscript naught will correspond to extremal things, values, and the energy will be close to J. So energy equal J corresponds to the extremal black hole. And there is a decoupling limit with a long ADS2 cross S1 throat glued to asymptotically ADS3 space. So this is the asymptotically ADS3 part. This is the what I would call the far region. And this is the throat very close to the horizon, which is here. And the metric here is ADS2 cross S1, where the S1 has a almost constant size. And this will be the phi naught, the background, constant background of the dilaton. If you look at the Penrose diagram, then ADS2 is a good approximation in this blue region. And this red curve just indicates that when I'm in this region, I can kind of neglect finite temperature effects. And then very close to the horizon, I have like a Rindler horizon, and the finite temperature effects are important. And the physics in the throat reduces to JT gravity coupled to a U1 field. So this was done in, well, this paper, and also more recently by Svetic and Ioannis, which studied the 2D models that emerge from 3D gravity in a lot of detail. Okay, so to finish this part, I will describe a little bit more the geometry. So we will define, so R is the radial holographic coordinate. Well, this is just to show some formulas in case you never saw this before. So we will take this rho to be our new radial coordinates in the throat. T is the inverse temperature that we are going to take to be very small. And if you take this and you put it in the BTC metric and you look very close to the horizon, you'll find that you'll have an ADS2 factor with an ADS2 radius given by the ADS3 radius L divided by 2. That comes from this prefactor. The horizon is at rho equals 1. Then this is the area of the horizon, the extremal area. And then you have this term that mixes phi with T. That this is where the U1 gauge field will come from, and we will think of this term as a background U1 gauge field in the geometry. So when I say ADS2 cross S1, I will mean metrics of this form. And this is glued to the region far away that is asymptotically ADS3. So to write the action that so the ansatz so we will do is a Kaluza-Klein reduction in the throat, and this is the ansatz that we will use. These are the massless mode in the metric, or the modes in the metric that will become massless at low temperatures. So this is the 2D metric in the TR coordinates. We have the dilaton, that is the size of the transverse circle. Phi is the coordinate in the circle. And this will be the U1 gauge field that it's independent of phi and has only T and R components. And when you plug these ansatz in the Einstein action in 3D, you get this action, which is of the form of dilaton gravity coupled to U1 gauge field. And okay, maybe this is a good time to stop. Continue. Thank you.
Thank you, Joaquin. So maybe there's like if there's any quick question, maybe.
I may have a question.
Please don't.
Just maybe quick question. So in this three-dimensional, BTG setup, basically this BTG can be embedded into standard ADS CFT correspondence, like ADS 3 times S3 times M4. So we know that this ADS CFT dual in a sense very well. And we have this particular ADS CFT correspondence. Yes. So I don't see any signals of ensemble average.
No, but that's why I said that this part will be based on the disk. So I'm not going to look at I will look at quantum effects in the disk. So it's like, and I'm not going to consider non-perturbative.
So non-perturbative is too much in a certain sense in this dimensional reduction.
Yeah, there are corrections that are too small to be trusted in general. So you should compute it directly in 3D.
Okay. So it's so you would like to say it's out of a validity regime of this KK reduction in some sense. Okay, that's good. Very nice.
Yeah, and as a comment for later, so what I will argue is that you can trust just quantum fluctuations around the disk. So this Schwarzschild mode, I think you can trust that, and I will mention about other non-perturbative effects that I think you can trust, but only when you do pure 3D gravity. So that would also be outside of the.
So the quantum fluctuation means the temperature correction, right?
Yeah.
Log term.
Yeah.
Okay.
Yeah.
Thanks.
Yeah, sure.
Okay, so
yeah, so I just want to say, I mean, I can stay around during the break in case anyone, if anyone has any question. I'll be
sure. Sure, and then so we take a break now and come back in half an hour.
Okay.